Question number 2.125. Find the efficiency of a cycle consisting of two isochoric and two isothermal lines if the volume varies V-fold and absolute temperature varies T-fold within the cycle. The working substance is an ideal gas with adiabatic exponent gamma. Okay. It means we need to write efficiency in terms of gamma, and there is a work substance that goes through two isothermal and two isochoric process like this. There are two isochoric process and two isothermal process in this case. Okay. So let's assume that in first case this is volume V1 and second it is volume V2. Okay. It is saying the question that volume goes to V fold. So this is V into V1, right? And second case it is saying that the temperature is going T fold. So if this temperature is for this line, let's take, if this is T naught or T1, whatever you take, then this would be tau into T naught. Okay. Let's take this is T1 and T2. Okay. So this process is taking place in clockwise situation, right? So at this stage there will be heat. Let's take 1. Okay. Again at this stage when compression is taking place here, okay, when pressure is increasing, then again there is heat entering. So two heat are coming into the cycle and there must be some heat lost. So let's take Q3 and Q4, right? So here we need to calculate first Q1, Q2, Q3 and Q4 before doing any further thing. So for isochoric process, okay, we can directly calculate Q because there is no change in volume, right? So let's calculate first Q2, this isochoric, and Q3 for this one. So if there is no change in volume, so there will be no work done, and from first law of thermodynamics, delta Q equals to delta U. Okay. So delta Q2 we can say that change in temperature. Okay. So Cv for 1 mole we are doing Cv into delta T and Cv delta T. So this final temperature is N tau, tau T naught, and initial temperature is T naught. So you can write once T2 minus T1, and this is Cv into tau minus 1 into T naught in first case. In second case here, please take a look at this point. Now again this is Cv. Now temperature is changing from T1 to T2, right? So we can write minus Cv, okay, tau minus 1 into T naught, okay, for this process. One volume is changing at this point, right? Now next, although we can take the number of moles, okay, let's not neglect this term, right? Now see, if we'll calculate for isothermal process, then work done in isothermal process is equals to nRT ln V2 over V1, right? And as temperature remains constant, so there will be no change in internal energy, right? So this delta Q is equals to delta W. So we can calculate delta Q1, or you can say Q1. So Q1 is equals to N R T1 or T2 here I wrote, so NR T2 ln V2 upon V1, right? So this Q1 is equals to NR tau into T naught ln V2 upon V1, so this is V4. So we'll get this. Similarly, for process Q4, this is nRT1 ln, final is V1, so V1 upon V2. So from here we'll get minus nRT0 ln V. Okay. Look, here you will put V1 and in denominator 1 over V into V1, so we'll get this term. Now we have all four heat that is in the system. So the total sum of heat is equals to work done by this cycle. So work done is sum of all heat Q1, Q2, Q3 and Q4. So let's add them. Whenever we add them, we will see that this term and this term will get cancelled out. Okay, this is positive, this is negative. So effectively we can directly write that it is nRT naught tau minus 1. Look, if you add this one and this term, then nRT ln V is common. So now we can calculate total work done in this process by adding all heat of the system. Okay, so this is Q1 plus Q2 plus Q3 plus Q4. Okay, so here you can see Q1 and Q2 are same in magnitude but sign is opposite. So these two terms will get cancelled out. In Q1 and Q4, the rest of the terms are same, only tau is different. So we can collectively write that total work is nRT naught tau minus 1 into ln V. Okay, so this is final expression for total work done. Now we need to calculate the efficiency. So efficiency is work done divided by the total heat supplied. So in this process, at two places heat is being supplied to the system. One is Q1 and another is Q2 here. Okay. So let's calculate heat supplied, that is delta Q in. Okay. This is Q1 plus Q2. Q1 is nRT naught tau ln V. Okay. So this is nRT naught tau ln V, and Q2 is NCV tau minus 1 into T naught. NCV tau minus 1 into T naught. So this is total heat into the system. Okay. So now efficiency is work divided by Qn. So from here we can calculate efficiency. This is nR T naught tau minus 1 ln V divided by nRT naught tau ln V is there as well, but this is NCV tau minus 1. So this CV can be replaced as CV is equals to R over gamma minus 1, as gamma is given adiabatic constant of this system. Okay, so we can write this is nRT naught tau minus 1 over nRT naught tau ln V plus nRT naught tau minus 1 upon gamma minus 1. So this term nRT naught is common everywhere, so we can remove from here. So efficiency is tau minus 1 ln V divided by tau ln V plus tau minus 1 upon gamma minus 1. And if required, then we can further simplify this equation, but this is an expression for the efficiency of the system.